Again, the purpose of a Riemann sum is to get the estimate of an area under a curve. And so if we're going to estimate the area under the curve y equals x to the third over the interval 0 to 1, we could get an estimate by breaking up the interval into equal pieces called a partition. And so if we do this first using a right point endpoint evaluation with n equals 4 rectangles, our red endpoints are going to be 1/4, 2/4, 3/4, 4/4, where the common width of each subinterval is 1/4. And the way that we do that is 1/4 is the common width going to be multiplied by each of the heights. And then therefore that would give you the sum of the areas of the 4 rectangles to give us an estimate of the area under that curve. And so the right endpoints being 1/4, 2/4, 3/4, and 4/4, putting those values into the function x cubed, 1/4 cubed, 1 over 64, 2/4 cubed, 8 over 64, 3/4 cubed equals 27 over 64, 4/4 of course is 1, which is 64 over 64, which is equivalent to 1. And then adding these together and multiplying by the common width on the calculator, we get an estimate of the area being 0.390625. Now, it may not be a very good estimate, however, it is an estimate. One way, of course, to make the estimate better is to have a different selection of the values in each subinterval so you don't have so much overestimating. Midpoint rule is an example of that. However, another way to make the estimate more accurate is to break it up into smaller pieces, and so you have more rectangles. So therefore, if we repeat this process again, but do this with 10 subintervals, you can see in the picture that it appears that although we're overestimating, we're not overestimating by so much, because we're breaking up it into 10 rectangles, where the rectangles, yes, are thinner, but there's more of them. And so selecting the right endpoints again, the common width for each of these thin rectangles is 1/10. So 1/10 the common width times each of these values, 1/10, 2/10, 3/10, 4/10, on up to 10/10. Each of them being cubed would give you the heights of each of the 10 boxes. So with each of the heights added together, multiplied by the common width, would then give you the sum of the areas of all 10 of those rectangles of all varying heights, that together would give you an estimate of the area under the curve y equals x to the third. So on the calculator in this case, we would get an estimate of 0.3025 as an estimate of the area under y equals x to the third. So whether it's a good estimate or not, it certainly appears to be a better or closer estimate than when we performed the exercise with only n equal to 4 rectangles. We could, of course, make the estimate better by even yet more boxes. Let's suppose we were to divide the interval up into 100 subintervals. With 100 subintervals from 0 to 1, the common width of these boxes that are so thin that it's hard to even distinguish them, we would know then that the common width is 1 over 100. So even if we can't view the picture very well, we can still do this algebraically. And in this case, it would take us, of course, a very long time to write down all those numbers. 1 over 100 cubed, 2 over 100 cubed, 3 over 100 cubed, all the way up to 1 over 100 cubed would take us a while. But we do have a shortcut way of writing that. The common width is 1 over 100, and this symbol, if you're not familiar, means the sum of. Add up all the numbers going from 1 to 100, where each of the values is, we short that cut by I, counting from 1 to 100, meaning we're going to add together 1 over 100 cubed, 2 over 100 cubed, 3 over 100 cubed, 4 over 100 cubed, all the way up to 1 over 100 cubed. And so that's a symbol that's simply saying we're going to add all of those together. And what we can do in order to evaluate this is, since we're really only concerned about the I cubes, we can factor out a common, again, a 1 over 100 cubes. So we really have 1 over 100 to the 8th power right there, 1 with the 8 zeros, and then the sum from 1 to 100 of I cubed. Fortunately, we do have a formula for adding up together the first 100 cubes of numbers. 1 plus 4 plus 1 plus 8 plus 27 plus 64 and so forth. And then that formula is, however many you're adding up, n, or 100 squared, n plus 1, 101 squared divided by 4. That happens to be a verified formula for adding together n number of digits cubed. And so on the calculator, we figure out that the estimate for this is 0.255025. And we figured that that estimate is going to be much better than the previous two because we did this with 100 rectangles, very thin ones, but 100 to fill in the space between 0 and 1. But of course, we know since it's still going to have that slight little overestimating on each one, it's still not an exact estimate of the area under the curve. But again, it is an estimate. Ultimately, our goal would be to have an exact value for the area under y equals x cubed on the interval from 0 to 1. So in general, if I say, well, if we divide it up into unspecified n number of boxes, the common width is simply 1 over n. And then the right endpoints, instead of being I over 10 or I over 100, it would be I over n, depending on what that number is. And I'm going to replace that with I over n to the cubed. And so this is the sum of the common heights of any number of boxes being added together. Add those up, multiply by the common shared width of each of the rectangles, and we've got a formula for finding the area with any number of n number of boxes, whether it's 4, 10, 100, 700 boxes, 1,000 boxes, 1 million, a billion. And then we can compute that with our formula for the sum of I cubes being n squared, n plus 1 squared over 4. So how would we get the exact area? Well, let the number of boxes increase without bound. And therefore, the estimate would get closer and closer and closer and closer and infinitely closer to the actual area. Evaluating a limit, we take the limit of this expression right here, and we would determine that as n becomes infinite, the true area is 1/4, or 0.25. And that's the purpose of doing the Riemann sum, is by taking any number of boxes or rectangles to estimate the area under the curve and let that number of boxes or rectangles increase without bound. And therefore, we would get an exact value of the area under the curve. In this case, 0.25. And you can see that our estimates were progressively getting closer to that final value.